Hello everyone, it's Steps Buffer here. A few weeks ago, I started a rope simulation project for my computer graphics course. At that time, I came up with a method to render objects with constraints. As you can see here, with this method, I can render ropes and cloth. I was actually quite satisfied at that time, but there are still some problems. The first issue is everything seems too soft in this simulation, and ropes seems longer than they actually are. And another problem is that if I go to another tab and then go back, everything will just blow up. Some people may already realize what's causing this problem, but it's just a computer graphics assignment, so I decided to move on. For the assignment this week, we are doing some 3D rendering, so I decided to upgrade my rope simulation project to a new dimension and fix those issues by the way. But before that, I want to briefly talk about how I simulate rope in my previous project. Imagine you have an object. How can you move it around the space with physics? You can first consider it as pure point with mass. Of course, it will have a coordinate. Then you can add a velocity data to it. In each frame, you just need to change its position based on the velocity. Everything looks great. Now, how can we add force to the object? Let's say if the mass of the particle equals to 1. When applying 1 newtons of the force, the object will also accelerate at 1 meter square seconds. The direction of the acceleration is the same as the direction of the force. We've all learned that in middle school. Now we have the physics board to play around. How can we build a rope? My solution was using Hooke's law. By considering other rope segments as springs, we can analyze the force applied on each segment. All we need to know is the distance between different vertices. In the example here, I set up a virtual spring with proper constants. We can easily calculate the tension force applied on the spring and simulate its behavior in the physics world. After that, you want to render a rope, you just connect all the nodes in a line. If you want to render a cloth, you need to connect each node with its 4 neighbors. Everything looks fine by now. But what's causing all those annoying issues? Let's first go back to the movement part. Now you have function fx representing the position of object at time x. Its derivative at prime x represents the velocity of the object. We all know that we can integrate f prime x to get fx. And in practice, to get position at time t, we need to integrate from x equals to 0 to t. In the rope simulation process, we've already know the position at time t. What we need to know is the new position after a small fraction of time dt. To achieve this goal, we can just take the integration from t to t plus delta t and add the result to the existing position data. This is actually where the problem begins. Let's say now you have a function fx equals to x squared. You take the derivative of it and you get f prime x equals to 2x. And now you are at time t equals to 1, so your velocity is positive 2. You can use f prime x to calculate your velocity and move it around, but computer cannot do that. Remember, in the simulation process, we are not taking derivative of fx to get f prime x. Instead, we are integrating f prime x to get fx. And computers have no idea what the f prime x will be, since it depends on acceleration just like we mentioned before. Also, there's usually no perfect equation to express the velocity of an object in real world. So for computers to perform integration in scenarios like this, we can first take a relatively small delta t, then multiply the current velocity by the delta t to get the next position. From the demonstration, you can already see the error caused by this method. Here, I choose a relatively large delta t for better visualization. In real-life scenario, this delta t will be much more smaller, but the error still exists no matter how small the delta t you choose. The method I just talked about here is called the Euler method. An article I read about rope simulation had a pretty straightforward demonstration showing how bad Euler method can be. Here you can see 2 celestial bodies are running gravity simulation. The red one is using the Euler method. The blue one is using another method called Verlet integration. We will just talk about that later. Anyway, you can notice that the red moon is getting further and further away from the planet. In other words, it's gaining more and more gravity potential energy during the process. It's physically impossible. Now let's talk about the Verlet integration. How does that solve the problem? Simply put, it doesn't. It just makes the problem smaller enough that you can ignore it. Let's take a look at our integration process again. Here, we can first focus on the integral. Notice that when we integrate it by parts, it will turn into this form. And during the integration of dx, we left a constant c for us to choose. We can choose whatever constant we want here. A wise choice could be negative t plus delta t. This is because when x equals to t plus delta t, the term in the middle will equal to 0. Then we can simplify this whole bunch of expression to just the delta t times f prime t. With the expanded version of the integral part, we can rewrite the original equation. You may find that we can perform another integration by parts here. In fact, we can do this recursively. By doing that, we obtain what we call the Taylor expansion of f on t. When you flip the sign before delta t, you get another almost symmetric equation. We can throw away all the terms after the term with delta t cubed. This is because they are too small to affect the final result, and nobody actually cares about them. Combining what we have here, we get our final result. This equation describes the Verlet integration process. Here, ft plus delta t is the position of the object next frame. This is what we want to calculate. Ft here is the current position. Ft minus delta t is the position last frame, and f double prime t represents the velocity of the object. Let's see how to implement this algorithm in practice. Start by creating a particle. We can set up some constants. Remember, the data we need for the simulation is the position this frame, position last frame, and acceleration. To move a particle, we can change its acceleration. This can be due to external forces such as gravity or tension force. Then we can use the Verlet integration method to calculate its position next frame. To move the particle, we first need to change the previous position, and then update the current position to the new value. Let's run the algorithm for 2 more frames. After we change the acceleration, the particle will still behave as expected. Let's see what if there's no more acceleration. It seems that the particle will keep moving. What if we change the position directly? Will that affect its behavior? Apparently yes, the particle changed the direction of its velocity. This algorithm works so well that it not only reacts to the acceleration correctly and precisely, but also pertains its physics behavior when changing the position directly. We first apply an acceleration for 3 frames. Then we change the acceleration and run for another 3 frames. After that, we remove the acceleration and the particle kept moving. Finally, it seems that the particle hits something and changes position quickly. This bouncing behavior is also simulated. Now we've learned the math, let's write some code. Now we have the code to guarantee higher movement precision. What about constraint relaxing? According to this paper published by Jacobson, we can push or pull 2 vertices based on their constraint. And this method actually solves the problem of ropes being too soft in my previous project. To see why, let me show you an example. Here we create a rope with 5 nodes and 4 constraints. Let's move one of the nodes and run the Jacobson algorithm. We check the first constraint and find its length longer than 1. So we move 2 nodes on the constraint together to get its length back to 1. Then we check the second constraint and found its length also longer than 1. So we move the nodes on it together. We can apply the same process on the third and fourth constraint. We now find another problem. We shifted the first node up for 2 units, but now it's dragged back a little bit. This issue is also easy to solve. We just need to only shift one of the nodes on the constraint if another one is fixed. But after updating all the nodes, you may find a new issue. The length of the first constraint is still longer than 1. And here comes the magic of loops. You can perform more than one iteration of Jacobson method each frame. And with more iterations, it's almost always guaranteed that you will get a more accurate result. As a comparison, in the old implementation, we update the velocity using Hooke's law. When we move the first node, we can only change the velocity of the second node. We have to wait until next frame for the second node to change its position, and it even takes longer for the third node to start moving. While in the Jacobson method, when we change one node of a rope, all the other nodes will be affected immediately. And now we have all the knowledge we need to build a class simulation. We can build a class with constraint relaxing using Jacobson method, and we can move all the vertices in the class using Verlet integration. Let's take a look at the final result. At the end of this video, thank you for watching. I hope you render well, and see you next time.